So my name is Kelvin Mpofu. I'm a senior researcher at the CSIR, which is based in South Africa. So in our research group, we investigate biophotonics. We perform biophotonics research. So our research looks at the application of photonics technologies to the diagnostics of diseases such as TB and HIV, which are very prevalent diseases in Africa. So one of my projects is the integration of quantum resources in our optical biosensors that we develop here at the CSIR, and that involves building single photon sources and integrating them with the optical diagnostic setups that we have in our lab. That's me in a nutshell.
That's fascinating stuff. So we're right into quantum research and the adaptation of photonics into, I suppose, it's pathology.
It's more diagnostics.
Yeah.
Yeah.
And the diagnostics of pathology, so identifying viruses and bacteria, etc. on that side. Fascinating stuff. So, Kelvin, let's hit you with your first question. What would you say was your defining moment that sparked your journey into quantum technology?
That's a really interesting question. So for me personally, I think I didn't have any singular defining moment, but it was more a defining period in my studies, really. So in South Africa, we have a fourth year called our honors year. So it's sort of like an extension of your 3-year undergrad degree, and in that honors year, you take on a project at the end of the year. So during the course of that honors year, we were introduced to a wide range of subjects, and one particular subject that or subject that interested me was quantum applications of quantum computing, which I took with Professor Francesco Petriccioni, who was a professor at the University of KwaZulu-Natal at the time. And in that class, he introduced us to the application of quantum systems in computing. And that was really fascinating to me, because throughout my undergraduate degree, I had only had that impression of quantum physics as this theoretical, mysterious study that that's just interesting for the sake of interest, and not really something that I had been thinking about as a tool that can really be used. So after taking that class, I undertook an honors project in quantum applications of quantum computing, but with a different professor, with Professor Thomas Conrad, who's also a professor there at the University of KwaZulu-Natal, where I was. So my project at that time was highly theoretical. It was, we were doing calculations, and I wondered if these theories could really be useful for anything. I mean, it was nice to do the theory. Then it turns out there was another professor, Professor Martin, who was doing experimental work with these quantum systems, and he was developing these these quantum setups in his lab, and actually doing real quantum experiments. And so I had a chat with him, and he brought me into his lab, and he had me playing around with a few things, with a few setups here and there. And at that point, I guess I got sold. I really got sold into it, because it started to interest me. It really piqued my interest to say, oh, okay, this is a real technology that has real applications, and all these theoretical predictions and models that we were developing can actually become a real device. And I think it was that period really that shaped, or that drove me into that space of quantum mechanics or applications of quantum mechanics.
Fascinating. Wonderful to hear. Um, Next question. So, quantum is often described as the next technology revolution that's going to, change the world. In your view, what will be its most transformative impact on society in the next decade?
Mm. So in my opinion, um, so initially, maybe I'll take us back slightly. Initially, when people were uh, developing the theories and the ideas behind applications of quantum technologies, like when people were thinking of quantum computing, we had we had this big dream of what a quantum computer was going to be, and the intuition people had at the time was it was this type of computing system that was completely going to replace the classical systems that we have today. But over the years, I guess we've become more humble, and we've realized that, you know what, a quantum computer is really realistically going to be more applicable for specific problems. So uh, my view is that um, quantum computing is going to be relevant for specific niche problems that we find modern or classical computers uh, don't solve very well. These are typically very complicated optimization problems or cryptography type problems. Um, so these are the big. That's where I think quantum resources might have a really big impact. But outside of the space of computing, we also have, quantum technologies being utilized in the space of sensing, which is, well, this particular space I work in. And we find that in sensing, um, there's this added advantage. There's a certain advantage that we have, which is that for sensing applications, we don't require as many as many qubits uh, to perform, valid tasks as you would maybe for quantum computing. For instance, for a quantum computer, you might need on the order of maybe a million physical qubits in order to you know to get the appropriate number of logical qubits that you need for to perform certain optimization tasks. So yeah, um, I think in the space of quantum computing, quantum sensing, uh, for sure, quantum communication applications are developing quite rapidly as well. And recently, um, we had some of our local South African people who are based in Stellenbosch, who were able to extend the range on for which you can perform quantum communication tasks, and it was a major breakthrough. I think that's Dr. Yassira at the University of Stellenbosch and Professor Francesco Petriccioni at the University of Stellenbosch. So there are major breakthroughs across the quantum space. I think if I were a gambling man, and I think I would bet on quantum sensing to probably be the more the easier technology or the quicker technology to get to market at the moment.
I can really relate to that. And obviously, cryptography is one of the first areas quantum computing will have well, just it's needed right now, from the threat sector that's there already. I think we'll see that within the next couple of years, definitely, going through. The sensing bit is really interesting because there's unlimited amount of applications for sensing that, you could apply to. on that side, from health in the area where you're working through to agriculture, through to uh, space and how can I put it? Looking at obviously climate and things like that as well. So there's so many different areas you can go into, as well as manufacturing, chemical, and that. So I can certainly see those areas. I think what I'd like to ask you is, do you see any ethical or societal changes around that transformation?
Um, I do. So perhaps maybe the first one that maybe I would like to flag that I think we are all sort of witnessing is at times, I don't know if it may not necessarily be intentional, but there tends to be hype at times with certain technologies as they develop. For instance, we find certain advancements that happen in the space of quantum computing can be oversold at times. Whereas, yes, perhaps there might be a certain breakthrough, but we get to points where people maybe exaggerate a little bit. The motivations perhaps uh, varied, but so I think for me that issue of there being a lot of hype behind certain developments and technologies can border on the premise of on being unethical. Then, in terms of certain perhaps issues that I see in the future, I think there might be companies where or organizations which will not be as prepared for, the post-quantum cryptography era, and just not being prepared for such an era can have devastating consequences, especially depending on the nature of the organization. And so the consequences can be far-fetched. For instance, imagine if your bank didn't, put in place protocols to protect against a post-quantum era. That would be that would be a very devastating thing.
It's a scary thought.
And I guess another possible issue that comes to mind uh, that comes to mind could be yeah, what is it? I had something in mind then. Yeah, so in terms of when I think back, in terms of countries in Africa, maybe under-resourced countries, uh, in Africa, access is really an issue, especially access to quantum resources. We find that there are instances where, where another, maybe other developed countries in Europe could easily access, quantum computing resources for particular applications, whereas, in Africa, just the cost of accessing similar resources uh, sometimes is beyond our own budgets. And yeah, so access challenges are also kind of something that could result in, you know, I suppose it could be an issue. Yeah,
Yeah,
that's what I'm trying to highlight. Yeah.
I can understand that. And obviously, the advantage of cloud delivered access to quantum resources is there and it's priced. You'd like to think as more companies and more organizations begin to use that, it'll become a cheaper technology to provide, ensuring more access. And, looking at partnerships for access as well is another great thing. I'd like to move on to a next question because there's lots I could respond on that last point for you. So, next question, question three. Scaling quantum from lab to real world application is a huge challenge for many organizations that are focused in the developments of it now. Just from your perspective, what's the biggest barrier you've faced and how have you overcome it?
Mm, yeah. Okay. So yes, definitely scaling, scaling, that shift from, from a lab prototype to a real world product is a massive problem. So the main challenges that uh, that we typically have are that quantum systems tend to be very sensitive to the environment around them. In a typical lab, you can navigate around um, some of these challenges quite not easily, but you have ways of navigating around certain problems that could affect your quantum system. So in my particular case, we develop these optical systems that integrate with these quantum optical setups as well. And the big challenges that we still face is that engineering aspect of taking our system from a lab to a real world environment, which tends to be noisy and messy, and thus interrupts our quantum systems. As so far in my work, I don't. I would say my work has really been more lab based, so I haven't really needed to overcome that big barrier of taking the work outside. But it is a barrier that is coming. It's definitely a challenge that is coming, and um, how I foresee um, overcoming such challenges is through collaboration with other teams. So typically, I'm more on the research side, and I think working with process people, engineering people who have those device manufacturing protocols in place. Um, could really benefit my work in terms of taking it from a lab-based system to maybe a system that we can use in in everyday life. So I haven't yet overcome the challenge, but it is a challenge we foresee in terms of our own work.
I, that's interesting that obviously you've had challenges and I get that, but you see the big one coming down the line and that's taking your work from the lab to the real world and into that environment where the environment itself affects the technology you're doing. Excellent. Thank you. I can appreciate that. And next question. If you could give one piece of advice to the next generation of quantum innovators coming through, what would it be?
Mm. So I have a few bits of advice. Um, I think the first bit of advice I would give to someone who wants to start working in the quantum space is always try to be learning. The space keeps changing so rapidly, and there's always something new to learn. So always keep in mind this idea of I need to learn, I need to learn, I need to learn. And maybe another piece of advice that I think is very crucial is um, this quantum space requires people from a wide range of disciplines, and we need to collaborate in terms of the wide range of skills that people bring in, because it's not a space for physicists alone. It's a space for engineers, computer scientists, social scientists. Everyone has a space here, and there's somewhere where you can find your place in the quantum world, the quantum space. I think those will be my two take home pieces of advice.
Good. Thank you for sharing. It's good to pass it on. Final question for you, Kelvin. Looking ahead, what collaboration or breakthrough excites you most about the future in quantum?
Oh, okay. So I have two main uh, things that excite me in the quantum space. One is the development of a quantum system that of a quantum computer that can solve optimization problems uh, better than a classical computer. And the motivation for this is that optimization problems typically have a wider range of applications in wide range of fields. And if we can solve classically intractable problems with a quantum computer, I foresee a major leap in the use of quantum computers uh, uh, in the coming future. The next big one is the development of uh, quantum quantum sensors that are robust and can actually give you an enhancement in the precision, whether it's in medical diagnostics, it's in navigation, or whichever area of choice. I think quantum sensing is yeah, it's near and dear to my heart. It's a field that I've been working in for the past 7 years or so. So it's something that I would really love to see develop in the near future. And I do think quantum sensing should come uh, as the first real solid application for quantum resources and quantum technologies.
You're a notable visionary now within quantum, being a quantum 100. So I'm dying to ask you this question, and we'll put the pitch here. So to help you get your quantum sensing to market quicker, if you could collaborate with any organization or individual globally, who would it be and why?
Mm, so for me, um, I would love to collaborate with Biocore, if because it's one of the companies that develops some optical biosensors that are similar to the ones that we develop. It's also a great company to collaborate with. I also have a few other universities in mind that maybe I won't name them, but um, so I think in terms of companies, it would definitely be Biocore. I would also like to collaborate with IBM because they do a lot of quantum machine learning work, which is something I also do uh, when I'm not doing sensing. So I think those would be the two big players that I would really love to collaborate with. Then I mean, they're the obvious big ones, the Googles who work in the quantum computing space. Um, those would also make a lovely collaboration. But off the top of my head, just Biocore and IBM would be one of the two of the big companies that would integrate the things I work with the best.
Well, you've pitched for it. Let's see if you get an email in the next day or two.
Fingers
on
crossed.
there. Kelvin, thank you for sharing. It's wonderful to talk with you, and we really appreciate your time to pull you away from your research and sensing to come and share with us your world experience with quantum. So thank you for those motivations, and we look forward to hosting the next episode. We'll speak soon.
Thank you so much, Drew. Thank you for having me on your podcast. It's really wonderful to meet people in the quantum space and just have a chat about quantum technologies, what the future holds, and it's yeah. Thank you so
It's a
much.
pleasure. Thank you for your time.
Thank you.